one person less is attending. I hope no one got scared by the fact that we are recording. But yes, hello everyone. So let's start with the official part of the workshop. I will start by sharing a small introduction to how we would what we would like to discuss today. So that's the overall goal, is to have this joint workshop between Hiperwind and TWAIN. And the idea is that Hiperwind, as you know, has for some years already been working on various, I would say, uncertainty related things, which some of it is related to also reliability modeling of wind turbine components, which may be of interest to TWAIN. But there's also potentially other topics, like there's cost modeling, there's other uncertainty quantification, there's also wake modeling. That all of this may be interesting, but right now today we should focus on the reliability part, as this is part of the TWAIN task 2.2, which also requires this type of research. So just a quick outline of the agenda today. So now we are past the first 10 minutes where we wanted to do this introduction, and then I think we can have a presentation of Esker on the main bearing degradation modeling, where, yeah, let's say we could use half of this time, 15-20 minutes, to presentation, but then also use the rest of the time to first round of discussions. Then similarly, we can look at Clément's presentation, who also has some more ideas about the cost modeling, which is in turn also relevant for TWAIN work package 3, I would think, or making a link between this work package 2 and 3. And then I think we can focus a very brief presentation of the TWAIN project, so that we then kind of transition to an open discussion where we try to find out if what are the actual synergies we can exploit. So thanks for this, for joining, and I think now let's give the floor to Esker.
Yeah, thank you, Nikolai. So let me see if I can share my screen here.
Great.
I hope you see kind of a presentation. Oops, let's just get that to the first one, right? And let me just duplicate this. Okay, one slide,
Right.
one presentation.
Yes, yep. That was good.
Okay,
thank
great,
you.
Thanks. Yeah, if something looks funny or changes, then just shout out. Or if you have any immediate questions, then let me know, and I'll try to reply the best I can. So what I'll be presenting here is sort of work we've been doing on a specific Siemens wind turbine 2.3 megawatt machine with a 93 meter rotor diameter, and looking into sort of can we, from the environmental and operational condition of this turbine in a specific wind farm, say something about what is the main bearing lifetime. There are some people here contributing to this, and I will just present this from the DTU Wind and Energy Systems point of view, but we have had many more contributors as well. Can I get to the next slide? So yeah, this is just a very fast slide of DTU Wind and Energy Systems, how it looks like. We are 4 divisions, a lot of sections, and basically I'm sitting in one of these sections down here doing this work. So if you ever wonder how DTU kind of looks and works, then you can have a look at this guy. But let's get back to the outline. So what I will present to you is a series of turbines, namely 27 of these 2.3 megawatt 93 meter rotor Siemens machines, sitting in the Teesside wind farm in the UK. They are owned and operated by EDF, the French energy company. And these turbines have sort of been the inspiration for how to try to evaluate the life of let's say, the components. And we will specifically focus on the main bearing in this presentation, because as I will tell you in a second, it is sometimes pretty hard to get detailed information of what is inside. Yeah, let me get rid of this. What is inside these kind of turbines? Can you see my mouse actually?
Yes.
Yes. Okay. Good. So what you see here is an image of a Siemens 2.3 megawatt turbine, and basically blades are sitting here. We have the hop, we have the main bearing in this position, and then we have the gearbox and the generator sitting at the back. And the reason for us focusing on the main bearing is that if the main bearing fails, you would actually need to unmount the rotor, and you would need a jack-up vessel for doing that, which is coming with a pretty high cost. So we have been sort of focusing on what are the most expensive drivetrain components to replace. And we believe that main bearing is definitely one of them. Another complicated component is the gearbox sitting here. But doing our investigation, we had a hard time getting, let's say, details on what is inside the gearbox of this turbine. So what we will be talking about is how we actually obtain the information about the main bearing and use this for the further modeling. So this is kind of a layout of the drivetrain scene going through. So this is the hop. This is the position of the main bearing. This is kind of where you see the gearbox, and the gearbox has 3 stages and a lot of bearings inside. There's a coupling between the gearbox and the generator. And the first thing we tried to do was to say, let's look at spare parts in motion and find spare parts for this, let's say, relatively old turbine. The Siemens 2.3 megawatt machine is probably like 15 years old in terms of design, maybe 20, you might say. And the good thing about looking at old turbines is you can actually see the spare parts. So we actually were able to identify that the main bearing is called, most likely is well represented. And I'm just saying it can be different, but it's probably well represented by an FAG 230/800 bearing. And once you know that, you can sort of look up into the catalogs of Schaeffler or other bearing manufacturers, and you can find out that this main bearing has an outer diameter of about 1.2 meter. The shaft is about 0.8 meters sitting in the middle here. It's a 2-row spherical roller bearing. So you have spherical rollers sitting here in 2 rows. You can see that the width of this is about 0.3 meters, and the mass of this main bearing is about 900 kilos. So this is giving you sort of a rough idea of what is this component sitting here supporting the main shaft. We did actually manage to identify some of the bearings inside the gearbox, also from the spare parts. We also, of course, managed to identify the gearbox specification from Winergy, but to get the details inside such a gearbox is what we kind of had to conclude was not possible in an open, let's say, fashion where we would be able to publish or publicly tell what we were looking at. So we had to restrain ourselves from looking into this, and we did not believe it made any sense to obtain this information under, let's say, very strict NDAs where no publications could or no reporting could be done. We did also identify what is the generator specification. So you can see here an ABB generator specification if you want to look into this. But for these reasons of not being able to get this information, we are kind of just focusing on the main bearing. Another thing you need to know about main bearings is, of course, what is the lubrication you need to put into these? And looking again for spare parts and let's say instructions on the internet on open sources, we were able to identify that the grease that you need to put into this main bearing is probably represented well by the Kluberplex, which is a bearing or a grease manufacturer called BEM 41301. So now the next thing we wanted to do was to get an aeroelastic model of this drivetrain to actually calculate what are the loads getting into the main bearing. So you can kind of see here, we have been sort of guessing on what are the distances between the different components of the drivetrain. And this was kind of then fed into a aeroelastic model. What I'm showing here is a how-to model, which is used for simulating the loads of the turbine. So just focusing on how the nacelle is represented in this aeroelastic code, you can kind of see that we have one element here where the hop is connected. Then we have an element here where the main bearing is sitting. This is an element where the gearbox is sitting, the gearbox rear bearing, and then we have the generator front bearing sitting here. two support beams are coming down, and we have sort of a bed plate representation here, and then this is actually sitting on the tower. So this aeroelastic model was used by a lot of other people in the Hiperwind project to calculate loads on the tower and estimating the life of tower components, you might say. Now, what we want to do here, or what we did, was to say we can actually, from the aeroelastic code, get what is known as the axial load and the radial load. So over here, I've been sort of drawing the axial load is like if you push the inner part of the bearing backwards, that will be the axial load. And if you then push the inner part of the bearing in any radial direction, that will be the radial load. So you can kind of say that, well, the thrust load of the rotor sitting here will be causing the FA, the axial load, and any sort of gravity loading is going to cause a downwards radial. And if we then have fluctuations on top of this, we will get additional radial loads in other directions. Now, what we will look into is how to use the, let's say, very basic ISO 281 standard for evaluating the life of bearings. If you can use the ISO 281 standard, then you can actually, from the bearing manufacturer, get some specification of what is known as the capacity of the bearing. So this is kind of how much load can this bearing survive. What you will also get from the bearing manufacturer is sort of what is the geometrical shape of the rollers gonna correspond to the equivalent load of the bearing. So you can kind of see that there's a factor saying how much what is the ratio of the radial force and what is the ratio of the axial force that you need to take into account in order to calculate the equivalent load, you might say. And this is also what you get from the bearing manufacturer. So once you have this, you would have to calculate the equivalent load by, let's say, averaging over different load levels in your time series. And basically, the scheme for doing that is kind of shown here, and is called cycle averaging, cycle averaging. So you need to find the load level of a certain number of cycles, and then you need to find how many cycles did you have at that load level, and then you're basically sort of averaging over this. What you also get from the bearing manufacturer is the exponent in the life equation. So the ISO 281 is telling you that the life of a bearing in terms of how many hours can you actually operate this bearing at a certain load here, PD coming out of the average load here, is related to the capacity of the bearing. So this C number is coming again from the bearing manufacturer. So if you plug in the C, you calculate your PDs, then you have to raise that to an exponent of 10⁻�3, which is again given by the ISO 281. You can sort of speculate, why do we have an exponent in this equation, which is kind of almost 3? But it's probably because, you know, what is inside this bearing is steel. And if you ever looked into SN curves of steel, that is usually coming with an exponent of 3. So it's kind of close to saying we have a lot of cycles loading some steel, and now we want to evaluate for how long will that last. Basically, you can kind of say that the front here is saying the life is estimated for doing 10 to 6 cycles. And now we're just normalizing by the rotation speed. So this is the rotation speed of the bearing in order to get from revolutions and back into time. So this will spit out how many hours will this bearing be able to operate at a given load and at a given rotation speed. So this is basically what we wanted to try to investigate. Is it possible to use the ISO 281 to get sort of an estimate of what is the life of this main bearing? It should be said that the diameter of this bearing is only 1.2 meters, which is really good, because then the ISO 281 is still valid. Once you get to bearing with a diameter more than, let's say, 1.5 meters up to 2 meters, the ISO 281 is kind of giving so many red flags that you can you can sort of put out the question: can you really use it? But and this is probably also a warning, saying if you want to look to direct drive generators with large diameter bearings, ISO 281 is probably not going to do the job. But for this specific turbine, we do believe that there should be a fair chance to use it. Okay, now the next thing we want to try to do is to characterize the wind classes of this turbine. So we want to investigate if we expose the turbine to wind class 1, 2, 3 with an average wind speed of 10, 8.5, 7.5. And if we specify the turbulence intensity with a reference turbulence intensity going from 10% to 18%, what would the what would the life of the main bearing then be? Here is an example showing that now we are using the aeroelastic code, specifying an average wind speed of 10 meters per second, a reference turbulence intensity of 10 or 14%. We are feeding in the wind, and then we're calculating what is the radial load, what is the actual load from the equation you saw before. And then we need to combine the two into the equivalent load. And this is basically saying we need to take the FR and multiply it by the X factor and the FA multiplied by the Y factor. And then we get this as the damage equivalent load. So what we see is that the load of the main bearing is basically a replicate of the thrust curve, which kind of makes a lot of sense, because we have, this is basically the thrust curve, but we have a high Y factor that we need to multiply to this. And that is why it is basically the axial force on the main bearing, which gets to the equivalent force of that main bearing. It should be said that we will also start to wonder what are the operational conditions. So we are saying the temperature of the turbines is 22 degrees. We're taking the summer period, and the cleanliness of the grease is kind of quantified as something called an EC value of 0.7. You can say 0.1 or 1.0 is the super clean, as clean as you can get. If you have a grease cleanliness of 0, it is super dirty. And yeah, and basically that has a huge influence on what the main bearing life will be, of course. Okay, but let's try to look at what do we get from the aeroelastic evaluations. So what we can plot now is the basic bearing rating in terms of years at the different wind speeds and at different turbulence intensities. So what you see is basically operating the wind turbine at 5 meters per second. If it was running like this, all 24/7 or always, then we would be able to operate for 600 years down here. But as we go for higher wind speeds, you can kind of see this is dropping fast. And as we get to 10 meters per second, this is where we get the lowest life, which is actually just corresponding to that. This is the peak of the thrust curve, and this is where the PD gets the highest. Once we get above the rated wind speed, then the bearing load is decreasing, and you can kind of see life is also coming up. So you can kind of see at 25 meters, we would have like 100 years of operation if we just run like this. Now, for the wind farm, we would have to specify the Weibull distribution, and we would have to say with an average wind speed of 10 meters per second, how many hours are we operating at 5, how many at 7.5, at 10, and so forth. And then we would have to average the lifetime of the different wind speeds by the probability of the Weibull distribution. And that is when we get sort of this kind of thing here, saying with a 10 meter per second average wind speed, if we vary the turbulence intensity, this is kind of what the model spits out. High turbulence will give a higher main bearing life, whereas if you decrease the turbulence, you would get a lower main bearing life. And you can kind of say that this is super counterintuitive for many people, because usually you would say, well, the more turbulent, the less life you have, right? But this is actually not what the model spits out. And the reason for that is simply if you sit at the rated wind speed, you will have the highest thrust force. And the highest thrust force is what will take down your or take the life out of your main bearing. And that is why if you have a low turbulence intensity, you're actually hitting this much more, let's say more hours per year, you're sitting at the rated wind speed, which is the really painful point. At least that's our explanation for this. Okay, so another thing we wanted to sort of investigate was the viscosity of the grease, the cleanliness of the grease. So again, what if the grease gets dirty? Then life really decreases fast. And the other thing is that the frictional forces of a bearing is causing heating. And the temperature of the bearing will have an influence on what is the viscosity of the grease. In many of these turbines, you can kind of say there's an auto-regreasing system, which is constantly pushing in grease from the cartridge I showed before into the main bearing. So you can kind of say there is a system trying to keep the grease cleanliness low. But once you start getting, let's say, metal debris particles into the grease, it will slowly decay, and the cleanliness of the grease will decline or decay over time. Now, in order to calculate what is known as the modified basic bearing life, you have an equation saying once you've calculated the basic life, you should multiply by this factor A ISO, which is saying if the cleanliness is getting small or getting bad, A ISO gets below 1, and your life will decrease really fast. And there's also a Weibull factor called A1, which is kind of specifying the failure level. So the L10 in this specification is a specification saying when 10% of all the bearings in a fleet are failing, that is what the L10 is referring to. But the A1 factor here can be used to change this 10 into something else for let's say, investigations of let's say, the reliability level of the bearing. Just a few plots. So we tried to do a temperature model showing what do we think the main bearing temperature is using the aeroelastic simulations. And you can kind of see that we expect to have a peak at rated wind speed again. The temperature comes down as we go to higher wind speeds. It will have an influence of the turbulence intensity. And now, again, you can kind of see that low turbulence intensity gives high temperature. High turbulence intensity gives low temperature, kind of meaning that you're fluctuating away from the thrust peak. This will have an influence on the viscosity. So you can kind of see viscosity is expected to change pretty much, again, as function of wind speed and again, as function of temperature. And if we try to now include all this, we can try to calculate this ISO factor. And you can kind of see that in principle at 5 meters per second, we would get, let's say, 22 times more life. But when we get to 10 meters per second, we might actually get into a region where the A ISO gets below 1. And this is mainly caused by, let's say, the temperature increase of our modeling or of this model. With these specific parameters, what we will then observe is that the life of around 40 years could decrease all the way to 22 as function of turbulence intensity if we would have this temperature effects. If we change the average wind speed, you can kind of see then we don't see as much a change in the life if we're running with a 0.16 reference turbulence intensity. Yeah. Let's go on. So what we tried now to do was to say, what if we include this A1 factor? Would we be able to sort of say, well, if the reliability level is tuned in such a way that it is one bearing out of 27 that is failing, then we can sort of draw a line here saying, you know, this is how long time we believe that we should operate before we would see the first bearing out of the 27 failing. And again, we can now plot that with different turbulence intensities. So you can kind of say if we're at high turbulence intensities, well, we would not even see one bearing in a 25-year design life. Of course, we could kind of say, what if we want to operate this for 35 years? If we have some lifetime extension, then we would kind of say, we would expect about one bearing to fail. However, if we go for the low turbulence intensity, then you might say, well, you know, one first bearing should fail here at like 10 to 12 years, next one here, and so forth. First one here, and then the second one. So this is 2 out of 27 bearing failings. Then we should expect that a little bit before 20. And you can say 3 bearings failing, that would be just around here. 4 bearings failing would then be around year 30 if we are running with the low turbulence intensity. So this is kind of how we interpret now this model. Okay, so I'll finish up in a second. So one question that was, of course, coming around is, we predicted around 70 degrees of the main bearing, which people and ourselves was also saying that's probably a bit too high. So we have sort of worked on a, let's say, more detailed thermal model of the shaft or of the main bearing. So you can kind of see the hub is sitting here. The shaft is now coming through the main bearing, but the main bearing support is now sitting on the bed plate. And basically, you can kind of say that both the hub and the bed plate will be the ambient temperature, so the outside temperature of the turbine. So looking a little bit more into this, we managed to formulate a little bit more detailed thermal model, and you can see some calculations here with different ambient temperatures. This is how we believe the bearing temperature should be. So we are expecting this let's say very low bearing life to be changed a little bit, and this is in progress. But what we have also done is to sort of look into more specifically this effect of that if you change the turbulence intensity, you get a lower life. So you have the basic rating of the bearing is now here. And you can kind of see here that the life is actually decreasing as we go to lower turbulence intensity. This is with, let's say, a lot more simulations than what you just saw before. So we do believe we have sort of mapped the peak of the turbulence intensity or the peak of the thrust curve in great details with this map, and it's not just an artifact of sampling the peak of the thrust curve. So we do believe it's a let's say a real phenomenon if you can trust the ISO 218. And I guess this is bringing me to the conclusions. It should be said we're just finishing up the work, and there are some details that I cannot share with you from the wind farm, because that is considered as not publicly releasable by EDF. But work is like finishing up in comparing what is the turbulence intensity of the Teesside wind farm, and also what is the temperature actually on that main bearing for all the 27 turbines. Yeah, maybe I should stop here, and then I might leave the word for Clemens to talk about the consequence of such an analysis. Should I stop sharing my screen?
Thanks, Asger. Maybe before we directly go to Clement, maybe are there any questions or clarifications right now? We can have more general discussion later, but maybe there's, I can see Tufe has a question.
Yeah.
Yes, just one small one. Maybe I missed it, Asger. It is just to understand, it's very clear how the sensitivity looks like when it comes to, failure or lifetime versus turbulence intensity, but the sensitivity to wind speed is a bit lost on me. Is it like for the entire Bible, or is it for a given wind speed that the TI sensitivity is more visible, or how does it work, like in a threefold correlation, if you will? Yeah.
Here you have the annual wind speed of the Weibull distribution. So this is kind of the change we see on annual wind speed. So that's not too, let's say, pronounced. And this is the reference turbulence intensity of the IC specification of the wind class. So that is what we see as the turbulence intensity is the major or the main contributor to this.
Maybe also one additional clarification. Actually, if you go to one of the previous figures, I think that we've been discussing that. I think that's more clear. For example, this one, yeah, this one that you had with the thrust and
this guy.
Yeah, for example, here what we see here is the dependence on wind speed, and it's really, in the end, the sensitivity is really closest to the point where you have the highest thrust force. So that's really, with respect to wind speed, this is really where it matters most. So that's in the range of, I would say, 8 to 12 meters per second. And we also see that if you look at the same plots under different turbulence intensities, this is also where you see the main difference between the life or the damage accumulation.
Yeah. So you can kind of see here that sitting at this point here at the top of the thrust curve, this is clearly where the load is the highest. And since we're loading this, or since we're feeding that into this raised to the power 3 power law, any change away from the peak will have a huge effect on let's say the life. So if you now imagine you're running with a wind speed of 10 meters per second all year round, you would be sitting exactly at this point constantly. Whereas if you increase the turbulence intensity, you might be sort of smeared away, and you will be falling down the let's say the tip of this this mountain here. Of course, you can kind of say that why would fluctuations cause us to go down this hill? But that is because the pitch system, the pitch controller, is kicking in, right? So if you're fluctuating around this peak here, on the right-hand side, the pitch controller will actually start doing actions, and that is what will cause us to have these, let's say, fluctuations bringing us down the hill. And one thing you should also remember that is we are not doing rainflow counting for averaging the loads. We're doing cycle counting. So we're asking how many cycles doing a 10-minute wind speed series are we sitting exactly at the top here? How many cycles are we doing at that point? But then we're also asking how many are we doing just at a point next to it? So that is how many cycles are we operating, just let's say 1, 2, 5% away from the peak. So that is basically what goes into this equation here. So the cycle averaging. And that is why you have to remind yourself that it is not a rainflow counting scheme, but it's a cycle counting averaging. So we are really reading off what is the load level of this curve here, and how many cycles are we doing at those load levels. Okay, was that answer enough, or?
Thanks. Yeah.
Definitely. Thanks a lot.
Rene?
Yes, one question. Did you have the chance to make some kind of validation against the real wind turbines in terms, I don't know, load measurements or of this kind?
Yeah, some. We cannot tell too much about it, I think. But what we have done is, of course, asking if we could get some load measurements, which turned out to be not that easy. So we don't have any load to compare to. So what we have looked at is what is the actual turbulence intensity of the wind farm, and compared that to the design, let's say, conditions. Because you can kind of say that the design conditions of the turbine is 0.16. So we're up here with an average wind speed of around 10, 8.5 over here. So this is the design point. And you can kind of say that, well, the turbulence intensity of this wind farm is probably lower, quite a bit lower than the 0.16, because we are, offshore. So you can kind of see that what we are speculating is, of course, if this wind farm should actually have the tendency to slide down on main bearing life. But I can maybe just without revealing too much information, say that the Teesside wind farm has not replaced any main bearings yet. But our model has not predicted any main bearings to be replaced yet. But it is also kind of reported that for EDF, they are very sort of focused on keeping the main bearings alive. And apparently they have a scheme for if they see any, let's say, vibration/temperature issues with any main bearing, they will flush all the grease out of the main bearing. So they will actually take all this grease here, flush it out of the bearing, and then re-grease the bearing after that. So they have let's say, a preventive maintenance scheme, which is probably much better than what you would get from the ISO 281. But of course, so the bet is we're saying 1 to 4 bearings should die in the wind farm during the 25 years of operation. They haven't seen any yet, but it remains to be seen if our model is kind of correct.
Okay,
but you
thanks.
can kind of say that we have not predicted 10 bearings should have failed already. So in that sense, the model and what has been observed in terms of how many main bearings have died is kind of still, yeah.
It takes years. Yeah.
Okay. One more thought, Esker. I think we're also trying to validate some of the assumptions, like the temperature models.
Yes.
I don't know if that's going to be a public deliverable, or how was it?
Remains to be seen. But clearly, the temperature model 2 is much closer to what is observed than model 1. We're just working on, let's say, model 3 currently to see if we can do a little bit better.
Okay. Yeah. Thanks. Let's then. I don't know if there's any other quick questions, or maybe we can keep the rest for like a more general discussion and move to Clément's presentation. And very thanks, Esker, for great presentation.
Okay, I'm gonna share my screen. Let me know when you can see it.
Yes, we see it.
Yes.
Now it's also in full screen. Thank you.
Okay, perfect. All right, so yeah, thanks for the presentation, Asger. So I'm trying to stay as interesting as you are, but yeah, talking about cost is a little bit more boring. But just as a piece of context, so like Hiperwind, I don't know how many of you are familiar with it, but it's mostly about like getting better at designing the turbine from the beginning to the end, to in the end increase the competitiveness of the offshore technology by reducing the cost. And everything is like by reducing the uncertainty throughout the process and also factoring in probabilistic design. So what Asger showed is that if we get like a very much more accurate model of the main bearing, then we're able to predict the failure more accurately, and maybe we can compute the plan for the maintenance in a more accurate fashion. And so on. And then there is the question that I'm trying to answer is what's the impact on the cost? So yeah, I apologize. I've kind of mixed slides from different presentations, so the template might not be super consistent. So I hope you will forgive me on that. But yeah, just a word on how do we measure the success in Hiperwind. So one of the metrics we're looking at is the LCOE, a very simple metrics, just quantify the cost that it is required to spend to produce a unit of energy. So behind the Barbarian formula there, we're just looking at the sum of all the expenses for a given year. We levelize that by the discount factor, and we normalize by the energy produced at the given year, also normalized by the factor. And so the good thing is that it's relatively simple. We could argue why if LCOE is the best metric, but it also kind of factor in all the aspects Hiperwind is looking at. So we're going to try to look at the capex reduction. So that's mostly by introducing probabilistic design and reducing uncertainty. So we are able actually to reduce the component mass, and so that the component is lighter, so it's also cheaper. On OpEx, it's about like getting better at predicting the failure and predicting the maintenance, so being more accurate on what is your window to access the site, and so you're not necessarily bound to doing your replacements in the June to August period, but you could do that in a more optimized way if you get better wind and wave data, and also if you know when your components are going to fail, then you can anticipate the maintenance and reduce the cost. And then there are also side benefits on saying, like, if we reduce the uncertainty on the AEP, the bank might be more trustworthy on the project, and we can hope that we can reduce the weighted average cost of capital by getting more interesting interest rates. And some ideas that also the DevX, but I don't know if we're going to quantify that in the end or if we have any way to quantify. And also, so those are for cost reduction, and we can also think about maximizing the production, especially on the OEM side. If we are able to reduce the downtime, if we can replace the components in a more efficient way, we can also improve the wind farm availability and increase the AEP. So we reduce the numerator and we increase the denominator here. And in the end, the targets we had at the beginning was about 9% of LCOE reduction. We'll see if we can get to there. But what I'm going to show today is how do we factor in those better modeling in the LCOE quantification. So for CAPEX, first, it's relatively simple. So Hiperwind is looking at probabilistic design, which means I'm speaking under the control of Nikolai here, so I hope I'm not going to say something too stupid. But basically, if you get better at predicting your loads, you will get a narrower distribution. And so and if you design for a fixed failure probability, which is the overlap between the load distribution you have and the material strength distribution you have. If your load gets narrower, you can shift your material strength distributions towards the left here, and that means like a lighter component, and you can you in the end get like a cheaper wind turbine. And so the deliverables from the work package of Hiperwind is a reduction in the mass of the tower and the mass of the foundation, and we can directly compute the impact on the LCOE because the data actually for CAPEX is the literature is pretty well documented. And also at EPRI we have a strong effort on quantifying the cost of wind technology, either onshore or offshore. So we get like a good breakdown, an idea of like how much a turbine will cost per kilowatt or per megawatt. And we also like to get a good idea on what's the breakdown, for instance, this is for an offshore fixed bottom. So you can see that's the structure, for instance, the foundation represent like a little bit more than 15-17% of the cost of the turbine. And so if in Hiperwind we can get 20% reduction on the cost of the foundation, which seems realistic, then in the end that will factor in as a 5% reduction in the CAPEX or something like that. So that's the first aspect. Regarding the OpEx, as I mentioned, there are like two main components we want to look at. Is what Asger is doing, like getting way better at modeling the components, so anticipating the failure, and which means you get like a clearer idea of the number of replacements you need to do each year, and then you can plan accordingly. And also there are like work package that focus a lot on prediction of the wind condition, extreme weather prediction, wind and wave, so you get a better time. You can get to really more accurate way of when you will be able to access the site and when will you be able to perform the repair. So EDF, they are working on an optimization tool that factor in those component failure and also the wind and wave condition to optimize the maintenance schedule. And in the end, you reduce the downtime of your turbine and you can also reduce the cost. Seems it's a bit more marginal reduction of costs because everything is in the end fixed. Like if you need to replace components, the only cost that change if you do it faster is the vessel cost, which is still a big portion of the cost, but apparently it's where we gain the most is mostly on the reduction of the loss production, so the increase on the AEP. Then the question is, how do we factor that in the LCOE calculation, just to see making like an optimization on a very specific task, which is replacing the main bearing, or actually I think EDF is working more on replacing the gearbox, because as Oscar mentioned, like there is not so much failure on the main bearing at the Teesside wind farm, so they're looking at the gearbox. And so how does that impact the OPEX overall? So for onshore, we get like a pretty good breakdown of like what's the OPEX look like. So that's kind of data from April's report, but you can also look at WoodMac. Yeah, you will get like similar, maybe the categories are a little bit different, but you get like to a similar breakdown. And you can say, for instance, if you're able to reduce your consumption of wind turbine parts, how much it's going to impact your OPEX. But what we have for offshore is much more scarce. It's actually most of the time everything is referred to this NREL study that they publish like every year, this cost of wind energy, and they split things between operating costs and maintenance cost, and you don't get like so much detail on which fraction of the maintenance cost is due to replacement of the main bearing, for instance, or replacement to the gearbox. So we need to be a little bit more clever than that if we want to be able like to take the inputs from the overwork package and factor that in. So what the concept we are developing is really to try to develop a simplified OEM model that takes as an input the component failure probability. So for each of the main components of your wind farm, you can get EPRI as a database, for instance, of reliability of turbine components, and we can make regression on that and know what's the Weibull distribution that predicts the component failure for the main bearing or for the gearbox. And from industry data, there is also, we can get an idea of what's the cost of the component from the CapEx, and shipping, labor cost, they can also be found in the literature. So we can quantify the component likelihood of failure and the failure impact, both in terms of cost and in terms of downtime. And so come up with a very simple way to, or very, I would say, simple OEM model to assess the cost and the operating cost. So basically, like for each year, the OPEX is going to be like the sum of the component failure over each of the components. Like how many failures do I have for that component, and what's the cost of the failure for that component, which will be breakdown in the material cost, the labor cost, and also the vessel cost for shipping the new components to the site. And with the failure probability, we're able to estimate. So what we run is actually like multiple Monte Carlo simulations where we split where we put inside the component failure, and when we get like time series yearly failure, and then we take the aggregate of that. And there I'm just showing like the breakdown per component. The data for the blades like needs to be updated. I realized after making that slide that there is actually in the database I'm looking, there is probably like a serial defect. So all the blades are changed at the same year. And so that gives that very weird Weibull distribution. So I probably need to go back and change a bit those parameters, but you get the idea. Like you know how many components you need to replace, you know what's the cost of a replacement, and so then that gives an estimate for your yearly operating expenses. And on the top of that, we can add fixed costs. So the operational expense are typically expressed as a fixed fraction of the total energy produced. That with a small manipulation, you can convert that into dollars per kilowatt hour per kilowatt per year, and also some other fixed maintenance. So in that case, I'm just using a fixed number, but we could also going into more detail and say what's the cost of a service action, what's the cost of just going there to reboot your turbine, and how many times do you need to reboot the turbines every year to get like a bit more granularity on those costs. And same goes for the downtime. So we know like what's the average downtimes per component failure, so that it's kind of aggregated data we can find from the literature on the time to go to sites, also the lead time to get to the new component, and then the time to perform the repair. So there, EDF is performing optimization, so we will be able to kind of factor in the real data for the Teesside wind farm for the component, the specific component they are looking at. And so we get like the total downtime per year. Then we assume this is kind of uniformly distributed over the year because the model is relatively simple. So we just get like a single metric for the wind farm availability, which is just like the ratio of the downtime divided by the total number of operating hours per year. And so that gives an extra loss that we can just scale down our AEP. So the net AEP is just including the internal losses, the wake losses, electrical losses, and other losses in the drivetrain, for instance, if we get a detailed enough model. And so that gives the net AEP, and on the top of that, we scale by the downtime, and we get to the effective AEP. And so with that, we have all the components we need to compute our LCOE. So we get the AEP that you can see can vary each year. So there, the only variations for the AEP is really just like the difference in component failure. So you can see like the operational cost increasing with time because you have more and more failure, and then your AEP decrease. Just because of that, we could also imagine more complicated scheme, for instance, where we will also take account for the wind farm, the wind resource variability, and get maybe a confidence interval of what the AEP can be for each year. But right now I'm just looking at a fixed AEP number. And so with the CapEx is fixed, we just need, once you fixed what were the financial assumption, you just split that between an initial payment and then a constant yearly payment. So that's not super interesting, but yeah, we see that we can get like the operational expenses that can vary with time. And then we factor that everything in, and we get an estimate of the LCOE, where mostly like the operation and maintenance take into account what's the failure probability of your components. And so once we have that, so that represents the baseline. We're just taking like the things before Hiperwind. And so what I'm currently implementing is like gathering all the inputs from the other work packages, and I need to update those slides with the most accurate figures. But the idea is that we will use for what Asger gave us for the failure probability of the main bearing to compute the actual operational expense. We will use what EDF is providing us as what's the downtime for the component, and that hopefully will reduce this operational box here, and on also the capital will be reduced by the reduction of the mass of the component. So yeah, that's the concept of what we are doing for the cost modeling. The idea is that in the end, this tool is also going to be made public. So we need to define exactly what can be gone public, because there is a lot of confidential information, for instance, on the OPEX, on the Teesside wind farm, a lot of it is confidential. Also, we are using failure data from our reliability database, which is a service we typically sell. So we might not be able to give the most accurate model, but at least we will produce an online version of the tool, maybe with simpler model in it that allows to compute the LCOE for any wind farm. So we've really trying to make this model also being as modular as possible, and we can replace each model and also increase the level of detail. So as long as the OPEX model spits something that the overall class understands, we can make the model here as complex or as simple as we want. So hopefully that will be a deliverable from the project. So I think that's all I had. So I'm just going to stop here if there is any question.
Many thanks, Clement.
So was I very clear or very boring?
I think Irene already has a question, so definitely.
No,
not
not
too
boring
boring.
at all. So many thanks. Well, you mostly asked my question in this last slide, thinking of the potential collaboration with TWAIN and how to not reinvent the wheel. So do you have any time schedule to make public this even the simplified tool, or which are your expectations there?
Yes, so I mean, like the Hyperwind project stops in September, so I will say September is gonna be the hard stop for that. Now, like the tool is, I mean, almost or the architecture is there. I'm just like kind of finalizing the last part of it. So if it's also like for, I will say, research purpose, I think I should be able to give you the source code and train you on how to use it. So I think it can be done relatively quickly, as long as we. Yeah, the caveat is what exactly can we share? But for instance, yeah, on the model, on the OPEX model, what is confidential is the failure probability. So we could also use failure probability that are publicly available in literature and then share the code and the logic, because I think what you're interested in is the logic and maybe not so much the failure data themselves. So we could use public data to give you an example of the code that works and share the code. I need to double check, but at least I think that should be doable.
And it is great that Nikolai is leading this part in TWAIN, so on the course. So he will make a good transient there. Thank you.
Thank you. You can see there's more questions from Pierre and then Tufe.
Yeah, thank you for the presentation. Could you please re-explain why the maintenance cost in function of the year of the blades have this particular shape? I think you told us that there was a mistake somewhere.
No,
Can you just
not necessarily. It's not a mistake. It's just like the database we have. It's a big database of what's the turbine model, and so you can drill down to platform level, component level, manufacturer, and even supplier level. So I just took the data we had for the T-side turbine, which is like the Siemens 2.3 megawatts, and so what we have is like the failure, when the failure happened, or maybe more precisely when the component was replaced after the COD, so like the number of operational year when the failure happened. And so what we had for this specific turbine model is that for the data we have, like all the blades were replaced the same year. So I think it's because they realized that there were maybe like a manufacturing defect or something, so they changed everything preemptively. So we get like a huge spike in the distribution. So then when we try to fit the variable, that gives that form. But I would argue it's not necessarily representative of like the component aging and the failure rate increasing with time. It's really at some point like the person operating the wind farms we had with those turbine model, they realized that they need to change all the blades preemptively. So I would say it's not what we get out of the regression to get the failure probability is not representative of the entire fleet of Siemens 2.3 megawatts that are in the wild.
Okay, thanks.
Tufe?
Yes, my question is also in the same slide, actually. So thank you for bringing it here. And thanks a lot for, I think it was not boring at all. Maybe we all like talking about money a little bit more than. So for this particular graph, I was wondering also for the blade replacements, how much of it is like, the unscheduled repair, how much of it is related to also, for example, with leading edge erosion and stuff like that, which we said also we wanted to take into consideration in TWAIN. Do you have that also here? As one of the reasons, as one of the failure components?
Yeah, like the database will have it, but I have not looked at that. So what I've done is just took the entire replacement and did not bother of the failure mode there. So it was really like to get some data to put into the model. And yeah, I agree, we need to think about it. So those data we do have in the database. We know what was the cause of the failure, but that I don't think we should be able to share because it's kind of the proprietary information from our members, and I'm not sure we are really able to disseminate that.
But regarding that, that's my second and last question for now. It is the failure probability database that you mentioned, which I can also hear that is very valuable. But I also have sort of maybe I'm a little bit in doubt because we are talking about particularly how the wind farm control itself affects the failure modes. This is the focus of TWAIN. So I'm a little bit questioning how much of this database would anyway have controlled operation data set, because it's not necessarily widespread, we don't know, and definitely it's not been implemented for years and years and years to see the effect of certain failure modes. So that's on that regard, perhaps we need to stay still on the lower TRL and more on the theoretical level when it comes to wind farm control's effects, but I'm wondering what you think about that.
Yeah, I mean, definitely. So those are things we are looking at. We are starting to look at just to also bring a little bit more granularity in that. So there is the effect of the control, that's for sure. Also, like, what's the effect of the site conditions? Because if you look at a component like the main bearing, as Asger mentioned, like it's really the wind speed is driving that. So if you're comparing two wind farms, one with 8 meters per second wind speed and the one with 10 meters per second average wind speed, you don't get the same failure. And so if you're kind of lumping everything into a single failure rate, yeah, you're probably increasing your error bars, right? So those are things, definitely, I think that those are things that are very valuable, and we have just start scratching the surface on that.
Thanks. Maybe I have also a quick question, or maybe two questions. One is about the blades. Do you all these data, is it for the same generation of the 2.3 megawatt blades, or is it for all the population? Because I think actually Siemens have several generations depending on the production year, and maybe this, if it's a defect, maybe it's also limited to one generation or something like that, and then we could filter about that.
Yeah, I need to double check because the way the tool works is that it does not provide you that information. So I need to go into the database and then extract the actual failure and have a look at. But yeah, I think it's really probably one generation, and then they realized that at some point, like there was a problem, and then everyone starts replacing the blades. There is also like a few other examples in the database that if you look at other turbine models from other OEM, there is a huge spike after a given year. So maybe at some point they realized that there was a problem and that things needs to be replaced. So it might be that the sample size is too small here, and we are biased by something specific.
Okay, thanks. And then the other question is on slide 10, you had the LCOE given in euros. So this one actually seems a bit above the standard target that you would have for, let's say, for modern wind farms, or the ones, at least if you make a call for tenders, you probably won't get too far with this cost. So I don't know if do you think that's the one actually that is valid for T-site, or how does it work?
Yeah, actually, that's something we'll need to discuss next week, because I think what's really matters here is that it's the wind farm is a 2.3 megawatts built on an offshore wind farm. So nowadays it's not going to be that. And if you think like what dominates, for instance, the operation, or at least how people typically model the OPEX, if you look at what NREL has, or also what Strathclyde is doing, it's the vessel cost. Like just the vessel cost is the 90% of the component replacement, just by how expensive are the vessels. So then, like your operational costs, they're just going to scale as a linear function of how many turbines do you need to install to reach a given rated capacity of your wind farm. And so nowadays people tend to go to 10, 15 megawatt turbines, and so they get like a given yeah, they get those numbers that you see here, and when they use, I think that's NREL data, and that's based on an 88 megawatt turbine, and in the latest, the 2023 version, they use the 15 megawatt turbines for the model. But basically, like at a constant failure component, if you say, okay, my wind farm of 600 megawatt, I'm just going to put like 2.3 megawatts turbine, then you multiply by almost 3 the number of failures, because you have three times more turbine. So then the question will be like, do you think the failure rates remains the same when you go to a 15 megawatt turbine, and basically you're outside of everything people know how to manufacture correctly? But yeah, I don't think we can answer that until we have more data. So to your point, yeah, it's above what we see in the industry, but it's also because we are looking at a very small turbine rating. And so, yeah, we'll need to think about, like, maybe what we need to do is to consider for Hyperwind delivery, maybe we need to consider a more recent and a more, I would say, state-of-the-art wind farm to compute the LCOE. But that's a question for the meeting next week.
Yep, thanks. Esker, maybe last comment question, and then.
Yeah, well, just a comment to this LCOE level. I think there's a paper sort of dating back to the first UK offshore wind farm saying Teesside is the most expensive ever UK wind farm, right? So you should remember it's many years back, and the support schemes for getting those wind turbine or farms to operate were really different. But this is also showing to you how much money they probably get in support now. And as that support is ending, they will transit into market operation, right? So it's yeah, it's a remedy of 15 years back in time or something like that. Yeah. But maybe just a question for you, Clement. I can't remember, what is the interest rate that you use for calculating this LCOE? Is it the low level now, or the kind of old high? Yeah,
I use the recommendation. I mean, I used what we had in April's research. So it's okay. US based. I should have them somewhere in another presentation. So yeah, it's those are there. So like it's a 3% interest rate. We have like a 60% debt and 40% of capital. So when you compute the weighted average cost of capital, I think it's something around 6%. Yeah.
Okay. Yeah.
Quite a lot. Yeah.
Which I guess is also a bit high for most projects today, isn't it? Or maybe before inflation, and now we're up again. I don't know. Yeah.
Yeah, that's actually the annoying part, because then you're like, we do all those things to kind of get better at the design and everything, and then you just change 1% the interest rate and you double your capex. And you're like, why do we bother?
Yeah.
Yes. Yeah. Okay, thanks, Clement, for a very interesting presentation. Again, I don't know why you think it could be boring when we talk about money, really. Yes, I think that's actually what everyone in the end is trying somehow to, also sustainability and saving the world. But I mean, somehow, I think if you also reduce the costs of anyone, then you're more convincing. So I think it's very good.
Thanks. A way to keep you interested.
So now, I have maybe also very small, let's say, overview of TWAIN. I don't know if I should do it or Tufa, unless you have like some 3 slides that you think that you could also give a very quick overview. What do you prefer?
I need to open them up. If you have something lying down, go ahead.
Okay, I'll go ahead with this. But it's I don't know if it's the best. That's why, I mean, I'm sure you have maybe the most up-to-date slides, but let's just go very quickly to tell you what is really the TWAIN project about, so that we can see how to connect what we just saw with how it can be utilized in TWAIN. So yeah, now going from Hyperwind to TWAIN. TWAIN is it's a project about data-driven wind farm control. So really the idea is or integrated wind farm control. The idea is how to use all the currently available and maybe develop a few new methodologies, mostly data-driven, in order to improve wind farm controls. But also, I think the main innovation is first that you go beyond the simple levelized cost of energy, power maximization, let's say, focus. Instead, you try to include multiple objectives, and this is one of the reasons why it's called integrated wind farm control, because you try to really include different data sources. You also include different types of models, both numerical models, but also these AI-based models. And then you also go for not only looking at a single objective like the levelized cost of energy, but you want to potentially include different things like sustainability, like social acceptance, or some biodiversity aspects. So all this together integrated in one also consideration in terms of how do you really integrate this into one software tool or one platform, one set of tools that you can use together so that you can pursue all these different objectives. So it's really kind of wind farm control that uses multiple data sources, multiple models on multiple objectives. How do you integrate all this together? And there is a slightly predominant focus on onshore rather than offshore. This is also because, for example, this is what we're talking about, some of the specific problematics like social acceptance, environmental impact, that's something that also is very, very important onshore. So the project has some work packages starting. Work package 1 is about how do you really integrate these data sources and how do you, it's really building this the platform on which you want to use all these, to integrate all these tools. So the starting from the data, but also later having modules, and how, for example, if you look at the AEP module versus cost module or something related to loads and reliability. So how do you integrate all this together? This is mainly the first work package, number 1. Then we have work package 2, which really focuses on these modeling the sensitivities or the impact of wind farm control actions. So if you change the yaw steering, or if you change the grid compliance, let's say actions, how does it affect other, let's say, performance of the wind farm in terms of, for example, power production and load accumulation? Or what happens if you do curtailment for bats and birds? How does it affect also the lifetime of the wind farm? So this type of interactions between different objectives or different KPIs, these are modeled in work package 2. Then work package 3 integrates this into impact assessment tool or impact assessment framework. So really we want to say if we have different these different types of control actions, their specific sensitivities, so how they affect the overall performance of the wind farm. Now you want to put all these considerations together into impact assessment in terms of multiple objectives, finding what is the what is, for example, what is still the cost, but what is also the effect of all these control actions on the lifetime? What is the effect of control actions on potential this environmental impact or social acceptance? And then all together combining these, how can you compare, for example, an action which maybe changes the cost but also changes the environmental impact? How do you compare these two, or which one matters most? Maybe it depends on the site and so on. So this is really this type of considerations are considered in work package 3. Also including the vulnerability / risk of the entire framework. Also, what is the if you have all these objectives, different data sources and different potential ways of working, can you really ensure that the system is robust? Yes, and then the work package 4 is on the decision support and on the use cases. So this is, okay, how can you apply this on some realistic use cases? And here we have, again, into today's meeting, we have Tufe, which is the project coordinator, and the work package 4 that the leader is Irene. And then we have, work package 3, that's where I'm responsible for, and then we have a lot of representatives from work package 2, where we actually mostly focused on today. Then also just to mention, we also have work package 5 is, I would say, mostly on communication and dissemination. I don't know, Tufe, if you want to complete what I'm just saying.
You covered it all. Perhaps again, just to highlight once more for the sake of this particular workshop, is that we're more interested, or we're mostly interested in the relative changes. So what happens between normal operation versus what happens when you're activating certain control strategies. So it gives us a little bit more, let's say, of a room, if you will, that as long as we follow the same assumptions to a certain extent, we don't have to have absolute values in a lot of the quantifications that we're planning to make. So we really are interested in how much increase, how much decrease, how much improvement, how much worsening, if you will, and having the trade-off between all of this. So that might be an important thing, again, to highlight how we are also approaching to damage and failure for the sake of this particular collaboration between TWAIN and Hiperwind. That's something that I think it might also be interesting for you guys, especially for the last to be made open or to be made publicly available modular toolbox that we saw. One thing we can help, let's say, with TWAIN is to add this control strategies, the settings themselves as inputs, which I assume that Hiperwind has not necessarily focused on at all, right? There is no control, right? It is all this like business as usual, normal behavior model. Exactly. So in that regard, that could be something that TWAIN sort of takes what you guys have been working on for the last 4 years almost, and then take that to the next level with a little bit more control strategies. That would be a really nice scenario for the damage and failure. In my eyes, at least, that would be really nice development. Again, like Irene said, we don't have to reinvent the wheel, and it would also be like a good collaboration, I think, since also we have a lot of common partners in both projects. So that would also be quite nice.
Yeah, thanks, Tufe. So I think this is like an overview of the case studies. Maybe we can also move further, because these are, it's just what related to what I was mentioning, that the case studies cover these aspects of environmental, social ramifications. Then since we talk about onshore, offshore, or mostly onshore, then we also need to think, can we actually adapt it to offshore? And then some specific case studies like how do you design your wind farm control, for example, on the next generation of wind farms. How do you say that you can both design the layout of the wind farm and the wind farm control together, so that you get the best, let's say, wind farm out of it? And then also that's for future wind farms, and then also considering that there's so many existing wind farms. So what can we gain out of for the existing wind farms in terms of, for example, this extension or repowering, so like the end of life decisions. So I think I would say, talking about the reliability, it could, in any case, I think it could apply to many of these use cases. Yeah, I want to also maybe have another slide on TWAIN Work Package 2.2, which is on this damage and failure the discussion which we are having today. So this is, I think, the one which really feeds into or links to the discussion on bearing, reliability, and O&M costs that we have. So this is just wanted to show you what this is about. So the purpose of the task is to develop these tools forecasting the damage and failure of various components. So I think actually somehow, at least if you look at some of this purpose, you can say forecasting the failure of various components, or in the future, or damage or the failure rates, for example, that could very much be the same as what we just saw for the main bearing that Eska presented. And then talking about what is really, what do we mean by forecasting damage and failure? You can see here that there's some different terms, like material degradation, damage accumulation, failure rate, and I'm thinking this may be somewhat different depending on the type of component that we talk about. Maybe if we talk about leading edge erosion, then it's material degradation. If we talk about tower or foundation, then it's the damage accumulation. maybe you know, talking about fatigue, and then if we talk about bearings, gearboxes, or other replaceable components, then we may talk about the failure rates or times to failure, just as we saw earlier today. So and also maybe as again, just to discussing what we earlier Tufe mentioned and I mentioned, it's really the impact of control actions on all these that is really the key question we have. So if you change any control action, how could it affect all these parameters? Because we, after all, the project is about improving wind farm control. So that's a very quick overview of the task. And then I think there's one more last slide, which says what do we want to do in more details. And then it says blades, support structure, drivetrain, leading edge erosion. And then there's some different partners that want to look at that. And then there's also so this is the failure mode prediction, or let's say prognosis of the time to failure. Then we have the fatigue accumulation in structural components. And then for some of it, as you see, I'm thinking of what we can get out. So for some of it, maybe is this component reliability sensitivity. What I'm thinking is it's really the one we're discussing now, which is like if you change the control settings or control actions, how does the expected time to failure of any of these components change? Then also for some components, we may also want to look at historical data if to the extent available, and look at this failure mode and effect analysis as a simple, let's say, risk screening. So that's the overall the view of how this task should go. As you see, it's not very detailed, and the project is starting right now. So we also want to make sure we get to a good plan or good start of what's feasible and what we should focus mostly on. That's a quick overview, and I think I have no more slides here. And so from now on, I think we can just have maybe an open discussion, if that's okay with everyone. Of course, if you have any questions specifically in task 2.2, please also go ahead. Tufe?
I might maybe kickstart the discussion / more questions to the Hiperwind team. What would you say the most important inputs for Hiperwind that we should also be prepared for? Because I'm guessing this particular task in our case is going to be depending a lot to the loads, which is another task for us, and how the loads are changing under different control settings. So those loads, these particular, or probably a number of channels selected, will have the highest impact for Hiperwind. So I'm wondering if you have the most important suspects that you think also the control settings do affect. Where do you think we should prioritize? Which load channels we should have a closer look at, given your experience throughout Hiperwind?
I don't know who wants to answer that. I can maybe start because I mean, so right now we have like any standard in Hiperwind. We're using load simulation tools which are standard, and I think they provide the same inputs you could get from any load simulation tool. And I would expect that in TWAIN we have the same or very much the same load channels available. So for the bearing, as we saw from Asger's presentation, I would believe it's the thrust force and maybe the rotor bending. So basically the main shaft loads, which are then considered as representative of the bearing axial and radial loads. Now I think the joker here is when we introduce wind farm control in terms of, for example, I think if we talk about derating or some kind of thrust control, I think that's pretty much, I think, using the same load channels. Then what you really need to change is the control settings into the simulation tool. This we actually have done in other projects, so I think that's fairly. Yeah, I think we know how to do it. With respect to yaw steering as potentially another control action, I think then it's still somehow related to, in order to, let's say, to talk about bearings and gearboxes, I think it's still going to be about main shaft loads. Maybe then instead of the thrust, maybe then the bending suddenly may have a bigger impact. I don't know, Esker, if you remember. So let's say I think it's still the axial force that was really dominating the load in this case, or was it also somehow the variation in the radial force?
What we saw was basically the phenomenon of thrust. So, I mean, that is sort of my main takeaway, because you can kind of say that the radial force that we kind of saw was basically just the gravity of the whole drive or of the rotor main shaft pushing down on the bearing, right, on the main bearing. But just maybe reflection on your formulation of your task, because I think my sort of, how to say, feeling now is that the way the bearings will fail is a purely statistical thing, right? So we're looking for the Monday model. So if we're installing 100 bearings, the only thing we can say is, you know, where we will have 1, 2, 3 bad ones, but where do they sit? We don't know, because we just picked 100 bearings out of the supply from the bearing manufacturer, right? So I think you should consider that there is the, let's say, prediction based on the fleet, but then there is the condition monitoring, picking out where is the bad ones. And condition monitoring is all about where do we have those 4, 5, or whatever bad ones. And one thing that you might, I don't know how much data you will get available here in your project, but if you do get some data from some failed components, which we did not get in Hyperwind, I think, then you might wonder if a life model, you know, should be switched from the nicely normal operating main bearing to now there's a main bearing with an issue. So maybe what you could do is to think of how do we degrade the capacity factor of this main bearing? How do we quantify? Now the grease will be contaminated with debris really fast. And then the evolution of this thing, once it is in a damage mode, is a completely different thing, right? So I think you need to sort of keep those two things as very separate things. And you might also sort of realize that once the manufacturer or once the operators are just seeing condition monitoring data doing something weird at some place, it just triggers, go and fix it. We don't, you know, there's no study, there's no waiting, there's no go and fix it. We, you know, and hence it's maybe not that scientific, but pure economy, as Clement is telling, right? We have an issue, get it fixed, order the component, get the boat, and then we just have to wait for the boat. But of course, as you're waiting for the boat, you might sort of wonder, how do we optimize energy production in the meantime?
Yep, thanks. I think that's actually very, it kind of triggers, and one more thought in me is, as you say, you have, these models are population based.
Yes.
And I think that's actually important to remark, because I mean, in principle, yes, if we talk about the wind farm where all the wind turbines are controlled in the same way, then we can make some conclusions population based. But then if we start talking about, you know, some more advanced wind farm control, then I guess guys that are really control experts, correct me if I'm wrong, but it may turn out that you typically do control actions on individual turbines. And that then you don't know exactly how, of course, what you know is, again, that maybe these turbines will have an increased or decreased probability of failure, but it's not necessarily that you can predict how this particular turbine will fail, because you don't know how, you know, if it's the good or the bad example of the bearing, that specimen bearing that you have on this particular turbine. So at least for validation purposes, I guess that's probably close to impossible to do. given the standard or the expected life of bearings. But
yeah, and the other thing, if you start thinking about it, how many wind turbines and how many wind farms do you actually need to build up a statistical basis for validating anything? I mean, you're probably into thousands of turbines to just purely get the statistics out of this.
Yeah,
is my feeling. But of course, you know, it's food for thought.
yeah.
I guess the failure probability database that Clement was mentioning EPRI has is partially addressing that, right? It's quite big. That's what I've been hearing. So it is quite a large database that has a lot of different probabilities from different turbine models, onshore, offshore, harsh offshore, maybe more vanilla offshore, whatever. So it might actually give us a little bit more. But you're completely right. It's not just for the failures you guys have been looking at in Hiperwind, but also we have been looking into the leading edge erosion. Forget about one turbine being different than the other. 3 blades in a turbine was degrading very differently under the same cloud over time, right? So it is a little hard to do those kind of estimations for sure. But we know the trend. We know rain and high wind speed causes erosion, and how we can avoid that. One way to avoid that is coming from control perspective is to non-regulate or do the axis induction by basically pitching, etc. So we are going to be following trends. You know, we just sort of, this is probably a good act. One more thing I wanted to ask that maybe you have not considered, or to what extent you guys have considered in Hiperwind, is the on-offs. So we have a lot of startup and sort of turn off the turbine situations, especially because of birds and bats, that we're taking the biodiversity into account. So like extreme shutdowns, let's say, but it's not under extreme weather. So it's just very sudden. So sudden shutdowns and a lot of startups, possibly much more in terms of its number, much more frequent than you would see in a normal turbine. In Europe and different parts of, and also in US probably, Pierre, when we look at the EDF data, we can see it there. So have you guys been looking into that? How do you think it is contributing to the cyclic load as opposed to rainfall counting, for example?
Who I can, or Clement, did you want to say something?
I mean, I don't have like very formal answer to that, but yeah, no, I mean, that will have been my point. Like, just need to be careful on if you start changing the turbines. Yeah, that's something you need to be careful. Is like, is it the failure mode going to stay the same, or if you start thinking of the control? So yeah, those thing of the bats is something that we had seen, like the guys trying to sell deterrent strategy where your turbines will shut down every 10 minutes or something like that. And so, yeah, I guess then it becomes kind of a budget allocation. It's something we had looked at in my previous life. I was working in hydro, and so hydro is really, you start the turbine, you operate at 100% efficiency, and then you shut down, and then they want it to. So you don't care so much about like the transient loading, and so I don't know if like those things also exist. If you typically, it's kind of a budget at some point. You say typically my life is 1, and I'm gonna spend 0.7 of my life is gonna be fatigue from normal operation, and then 20% is gonna be from those startups. And then like if you suddenly multiply by 10 the number of startups, then you need to ensure that you reduce the other parts, or you make your components bigger so that it can withstand everything.
But to quantify that 20% versus 7, the examples, that is a tricky part, no?
Yeah, I mean, like if it's fatigue, it's a matter of counting the cycles. So if you say, okay, like if I'm gonna start, for instance, in tower base, I think like it's the thrust, right? So then it's the variation of your mean thrust. You go from 0 to 100% loading, and that gives you the cycle amplitude. And so then you can at least get a sense on that. Like if you multiply by 10, you have like 10 more cycles. What's the Euler slope you will use for a steel base component at the slope? And I think that's a simple model that already gives you relatively good information.
Yes, go.
Well, I mean, we had a look at that for the main bearing in deliverable 5.2, and we actually went through sort of what is the life of the main bearing just running normal operation. Then we added the startup, the shutdowns, and we also added the grid low voltage right through, right? And the conclusion we got to, at least from the main bearing perspective, is any operation taking it away from the rated wind speed is good for the main bearing. So we actually saw that the main bearing light came up doing all these shutdowns and startups, because you're not sitting at that painful peak. So, I mean, I guess the question depends entirely on what component you're looking at. So from main bearing point of view, you know, go ahead, do the shutdowns, the startups, and we're happy, at least with the modeling we've seen, right? So I think it depends.
Yeah, exactly. That was actually also my point. Thanks, Aska. And yeah, pitch bearings may not be so happy about it. And maybe just to add one extra thing is we also are looking, we have data from the T-side wind farm. So we are looking at it. And one thing, as Esga mentioned, was looking at when we look at startups, shutdowns, low voltage write-throughs, we were also looking at what's the frequency of these events at this wind farm. So we were looking at, I think it's actually the one, for example, for the startups and shutdowns, the vast majority of those, they happen at cut-in wind speed, which is because it's you know, it's when the wind speed goes from 3 to 4 meters per second and the turbines decides that they can cut in. And then at some point the wind speed drops down again, they cut out again. And this happens many times. The IEC recommendation of 1,000 startups or shutdowns per year as simulation for the life seems to be not too far from the truth. As long as it comes to these normal startups and shutdowns. What else? So we are using also this information together with the normal operation information to establish what is the damage accumulation, historical damage accumulation in the wind farm. But so for the wind farm control, I think for the wind farm control, you can use, I think, similar techniques, just adding the numbers as Esga said. So, but I think that could be, it could have some relevance for fatigue. But I'm also thinking about pitch bearings or brakes. I don't know how much the mechanical brake is applied, for example, when you have this bird and bat protection. So I think, yeah, that's a very interesting question, which Hiperwind didn't consider at all. So these frequent, or if you need to change the frequent startups and shutdowns, especially if they also happen at other wind speeds than just cut in and cut in. Yeah, I think I don't know, Irene, you have maybe next comment.
Yeah, was around this discussion that you performed some analysis on the different effects and so on. And did you study just the main bearings, or did you look at other components and possible trade-offs in this sense? As you were commenting, for instance, the pitch, the pitch with respect to the main bearing.
No, I think maybe, of course, Esga could give more details, but just to quickly say that just as any other project, in order to win the project, you have to promise everything, and then you only have time to, or almost have time to complete what you have promised. So no, we didn't have the chance to look at pitch bearings because we had, considered main bearings as a primary component, and also there was actually electrical components that were considered with respect to how the entire drivetrain behaves when you have, for example, grid events like low voltage write-throughs or shutdowns.
Yeah, in this sense, for instance, is this something that with the information that Clement was presenting on the LCOE, which is the main driver in this sense of the OEM impact of the failures, any of the components?
Yes, so I mean, like the numbers I presented were relatively dummy, so I will need to update. So that, yeah, that's gonna depend in terms of cost. then, for instance, like the responsibility with downtime and cost is not the same. So it's also depend on what you're going to look at, like just the cost of the replacement. It's going to be the component that's the most expensive, but like if you have component that fades more, but it's relatively easy to replace, but it's going to contribute more to the downtime. But yeah, definitely if you have the framework, then you can try plugging in different numbers and see how does that impact. I don't know if that answers the question.
Yeah, it's well, if you had any insight in this sense, but I guess it's more example dependent, right?
Yeah, exactly. It's going to be very site specific and platform specific. So.
Okay.
Eska.
Yeah, and maybe just a comment to the pitch bearings, because the pitch bearings cannot be modeled by this ISO 281. So you need to do something more, detailed and more specific, because the pitch bearing is not moving very much, right? I mean, we're sitting at the optimal pitch angle most of the time, and then once in a while we are pitching out 90 degrees to stop the turbine or something like that. So we did not include that in this study. So we will not be able to answer your question in terms of trade-off between different components. But I mean, it's also a matter of, let's just say, the strategic decision of the owners, because what we hear is that it seems like EDF is just now saying, let's replace a certain number of gearboxes every year to make sure we don't get problems. So of course, how do you compare such a strategy with your model is getting a little bit complicated as well.
Yeah, you're fully right on that.
Super.
I fully agree on the point that it's all about the money in the end, and sometimes it's just replacing them is much cheaper than waiting for them to fail and then having to pay for unscheduled, etc. One of the good side about TWAIN, like Nikolai said, is that we have a majority of our focus onshore, so we're not that worried about the cost. At least we don't have to wait for a boat, but still, we might also be facing a lot more loads because we are talking about wind farm control literally stressing the turbines themselves, and what is going to fail can also be anybody's guess, especially if we end up not necessarily gaining that much power to the wind farm, then our business case is over, right? So that is the whole idea anyway. So I can see we have about less than 10 minutes right now. One thing, coordinator hat back on, I wanted to ask is that T-side is an EDF site, isn't it? And since you guys have been working on that very closely, Pierre, perhaps that's a question you can take to your team. Maybe we can actually at least get a little bit better access to the information regarding T-side and its analysis in TWAIN. Would that be possible?
Really, I cannot answer right now, because as you know, for TWAIN project, the entity that is operating the wind farm is the US part of EDF Renewable and not the European one. And T-side is located in the UK and is operated by the European part of EDF Renewables. And that's why I'm really not sure that we can give some information about the T-side wind farm in TWAIN project, because it's not the same part of EDF that has contracted with TWAIN.
Sure. But perhaps you can ask.
Yeah,
The worst they can say is no.
Yes. Yeah, for sure. I'm open to. I'm gonna ask the question. Yes, but I cannot tell you right now. Yes, it's gonna be okay, or no, it's not gonna be okay. Okay.
No, of course not. No.
Yeah, but I'm gonna ask also questions about some things that are some assumptions that you made about the gearbox replacement and about the blade replacement made at T-side, because it's really surprising what you're saying about, okay, all the blades were replaced in 1 year. I don't think it's the case.
It's not T-side. It's not the T-side wind farm. Okay. Yeah, it's what we have in our database. It's not the T-side wind farm. So
okay. And about the gearbox policy also, it's also surprising. But I'm not working for EDF Renewable, so I'm not aware of the strategy that has been decided in the last year, you know.
But just to the database that they have is for the entire fleet of 2.3 megawatt turbines, or not the entire fleet, but a very large fraction of the fleet of the 2.3 megawatt turbines that exist around the world. So it's just general statistics.
Yeah, but it's quite surprising because generally it's really expensive to replace blades. It's generally the choice that is made is to repair them. So that's why it's surprising. But why not? I don't know. It has to be checked from.
As good.
Yeah, maybe just a warning from our side, Stefan, that you know it is super complex or hard to compare. I think the EPRI database on thousands of turbines to a case where we have 27 turbines in a completely different environment in a different country.
Yeah,
because
absolutely.
I guess the EPRI database is US based, whereas the T side is UK, right? And the EPRI database, and Clément, maybe you should comment as well, is most likely onshore turbines, whereas we're looking into offshore. So, and what we have discussed internally in Hiperwind is exactly this sort of check of where are we in terms of failure rates, and it does seem, and maybe I should be careful what I'm saying, Clément, that maybe you should comment as well. It does seem that the EPRI failure rates are higher than what we have sort of picked up from what we hear from T side, right? Probably due to the fact that the EPRI database is onshore and T side is offshore, right? So any maintenance is much more expensive for T side than it probably is for the average EPRI wind farms. So be careful, and you shouldn't take this as a you know this is how it's all done. I think it's very specific, and the reason why I think that you see a pretty let's say upfront replacement of gearboxes for T side is that they run with this extremely high subsidy rate because they are on this very old subsidy scheme, right? So it would mean that if you are not producing, you will be losing your subsidies, which is way higher than the energy price. So I mean, this wind farm is in a little how to say, maybe not again, I have to be careful, not a fully market driven or it's a special market they operate in, right? And for that reason, it probably pays off to say, just to get the last 4 years of production, we can pay off the replacement of a pretty high number of gearboxes, I think, even though we don't have any suspicions that they will fail. This is just upfront preventive, you know, being in good time to make sure that we get the subsidies that was promised. Does that make sense, or?
Yeah, for sure. Okay. After the maintenance strategy is also highly country dependent, and the way Europe is doing is totally different than the way.
I think you should also
US
see that it's very wind farm specific, and it's super specific to the subsidy schemes by which that specific wind farm is operating, right? Because this is going 15 years back. That was the contract they signed with the UK government.
Yeah, for sure.
Which is, you know, you won't find it today anywhere, I think.
Good.
Yeah, totally.
Okay. Many thanks, everyone. Any more last summary comments? I think it sounds like a very we had a very good discussion. Also, there's some ideas, some also challenges as we see. So I'm wondering if there's any follow-up steps that you would suggest, apart from, let's say, following.
I do have one suggestion.
Yep. Tufe?
Just a hands-on. I think that would give a lot of us a lot better idea, or maybe it's just me and the way I learn. When the prototype, let's say, of the final deliverable Clément was showing is going to get into place, perhaps it's a please feel free to use us as one of the deliverables. Again, that looks very good on the final project report, but please use this group again as a guinea pig for this, and maybe organize a small workshop so we can all do a little hands-on and get to know the tool a little better, because it seems to me, and it sounds everybody seems to be on the same page, that we don't necessarily have a better idea about how to start this task, and the idea is to really build upon your efforts, and Clement's modularity or the modular toolbox seemed like the way to go. So I think maybe that's a concrete follow-up when we're closer to September, your deadline.
Yeah, we can definitely have that. I was trying on thinking about the when, sorry. So yeah, like we need to publish, June is gonna be tight because we need to publish the deliverables. So then it's summer. So yeah, I guess September is reasonable.
September is the reasonable time to think about it. I agree. Well, that's great. Many thanks, everyone. So I think we can.
Thank you so much, Nicola.
Yes. Thanks everyone also for joining, and thanks also for Eska and Clement making the effort again to join us and have this presentation. I know both of you are really busy right now with finalizing these deliverables we're discussing, so it's good that you could put away these 2 hours. But I think that's also important as really a way to make sure we get we use the results from Hyperwind in other occasions. So I think that's also very useful exercise we're doing now. So thanks again, everyone, and have a good day.
For organizing.
Yeah, thank you.
Thanks for organizing.
Good luck with
See you in
Dublin.
Dublin.
Thanks.
Nice
to see you.
So see you in Dublin. Indeed, yeah, the final event of Hyperwind. Before we close, the final event of Hyperwind is in Dublin on June 11th. Together with this Wind Europe Technology Workshop. So if anyone happens to be passing by there, please just join us. And there's a registration form you can find on the Wind Europe site. Yes. Thank you. Take care.
Please have a Guinness.
Bye-bye.
Bye.
Bye.
Bye.